x1 plus 2x2 less than equal to 12 and x1 plus 2x2 less than equal to 6. And this x3, x4, I have taken as an slack variables to making it a equality constraint. So original problem was 3x1 plus 2x2 less than equal to 12 and x1 plus 2x2 less than equal to 6. And x1, x2, x3, x4 should be greater than equal to 0. That means non-negativity and also integer. These are the constraints. Now, this problem, this in cutting plane method, if you have to apply, if you solve this algorithm says that initially the problem is solved by relaxing the integer constraint. That is all the variables are assumed to be continuous rather discrete in nature. Discrete means that we are considering only integer variables 1, 2, 3, 4, 5. But continuous variable, it can be fractional value enable. That means it is a continuous in nature. So here initially we are ignoring the integer constraint, and the problem we can treat as a normal linear programming problem, and decision variables can be any value, can be a fractional value. And this can be solved using simplex method. So we can solve, as we have already discussed, how to apply, how to solve a linear programming using simplex method. So the simplex method, once again, just a starting solution, we have formulated the initial simplex table, and it was row 1, that means row x1, with that your first constraint, and then your for second constraint row 2. And we are right, initial solution, we are equating x3 is equal to 12 and x4 is equal to 6. And we are assuming x1 and x2 equal to 0 in the initial solution. We have started from the origin. So this is x3, x4 in the initial solution. It was these are the basic variables. So that's why these are under the basis. And this is the format as we have already discussed how to write a simplex table. So x1, x2, x3, x4, all the variables. And this is the right hand side. This is the solution. So this was the initial table. Now, this is not the optimal solution. We have to search. This is a feasible solution. That means we have started from the origin. So we have to search the optimal solution. And in the simplex algorithm, first we have to identify the entering variable with a maximum negative value coefficient in the Z row. And this here it is a under that your basic variable x2, there is a maximum negative coefficient under the Z row. And this is the entering variable, x2 is the entering variable, and we have we can determine this is the pivot row, and we can determine the ratio for that your right hand side divided by that your pivot column. So this is 12 by 12 and this is the 6 by 2. So the minimum value will be that your leaving variable, departing variable. So we can accordingly after first iteration we can derive the revised simplex table, and this x4 is replaced by this x2. X2 is the entering variable and x4 is the leaving variable. And this is new pivot row is equal to old pivot row divided by the pivot coefficient. So this is 1 by 2. This is 1. This is 0. This is 1 by 2. This is 3. So this is what we have written. And the other row is equal to old row minus pivot column coefficient into new pivot row. So that we have already discussed how to solve that simplex linear programming using simplex method. So we have derived the other row also, that means row 1 and row Z accordingly Gauss-Jordan transformation equation. So this is the in iteration 1. Still we can find there is a negative value in the Z row. That means it has not been reached the optimal solution. So again we have to identify the negative one. This one is the only option under this basic variable x1, non-basic variable x1. It is that negative coefficient in the Z row. So this is the entering variable. And the departing variable accordingly the ratio we can determine that right hand side divided by the pivot column, and this is for row 1 it is 3 and for row 2 it is 6. So this is the minimum one. This x3 is the leaving variable and x1 is the entering variable. Again using the similar process, the new pivot row is equal to old pivot row divided by the pivot coefficient. That means this is 1, 0, 1 by 2 minus 1 by 2, this is 3. And other row is equal to old row minus pivot column coefficient into new pivot row. So this is again we can do. And this is the after iteration 2, this is the revised simplex table. And you can find that non-negative values all the coefficient in the Z row are non-negative in nature. That means optimality has been reached and as well as the feasibility is maintained. So this is the solution what we got. X1 is equal to 3 and X2 is equal to 3 by 2. And if you recall that when we solve using the graphical method or the branch and bound algorithm, we got that initial solution was 3 and 3 by 2. So it was, we are ignoring the integer constraint. That means there is no mandatory, we are relaxing that X1 and X2 should be an integer. And what solution we got? The optimal solution, X1 is equal to 3 and X2 is equal to 3 by 2 and Z is equal to 19.5. If you recall that the same solution we obtained using the graphical method, if we are with not considering that integer constraint. Now, the optimal solution is a non-integer in nature. If we have to search now from here that an integer solution, all the decision variable as an integer. So this is that violating the constraint of integer and thus integer solution need to be searched. So we will apply here a Gomorrah-Kart method, and in this Gomorrah-Kart method we are adding new constraint, new cutting plane in that original problem, and then we have to search an integer solution. That means we are narrowing down our solution space, feasible region, to obtain the optimal solution, optimal integer solution. Now, how can we derive the integer solution? How can we derive the cutting plane? Now here you can see this is the optimal simplex table without considering the integer constraint. So this is the final simplex table what we got. X1 is equal to 3 and X2 is equal to 3 by 2 and Z is equal to 39 by 2. Now we have to search. We can get from this final simplex table, we can derive, we can write these equations: Z plus 3 by 4 X3 plus 7 by 4 X4 is equal to 39 by 2. X1 plus 0 X2 plus 1 by 2 X3 minus 1 by 2 X4 is equal to 3, and X2 minus 1 by 4 X3 plus 3 by 4 X4 is equal to 3 by 2. This is for Z row, this is for X1 row, this is for X2 row. The above constraint equation can be used to derive the cut provided its right hand side is fractional. So we will only consider the constraint, the equations which is having a fractional value in the right hand side. So if you see the second row, it doesn't have any fractional value. So it should not be considered to derive the cutting plane. So out of this Z row or this X2 row, we can derive the cutting plane. Now, how can we do that? So suppose, for example, in the Z row, equation can be rewritten as Z plus 3 by 4 X3 plus 4 by 3. We have written this was 7 by 4. We can write it is 1 plus 3 by 4 X4 is equal to 19 plus 1 by 2. And moving all the integer components to the left hand side and the fractional component to the right hand side, we have Z minus 19 plus X4 is equal to 1 by 2 minus 3 by 4 X3 minus 3 by 4 X4. So this is in the left hand side. If you see, this is X4 is an integer, and if Z is also automatically, if this is an integer value, this Z will be also an integer. So all the values in the left hand side are integer. So the right hand side should be also an integer value to hold this equation. Since X3 and X4 are non-negative in nature, both the fractions in the above equations are positive. So this is X3 if X3 is greater and equal to 0 and X4 greater and equal to 0. So obviously 3 by 4 X3 will be also greater and equal to 0, and 3 by 4 X4 will be also equal to greater and equal to 0. And if you subtract this 3 by 4 X3 plus X4 from 1 by 2, and this should be an integer, then only thing is that it should be less and equal to 0. If this equation, if this value should be an integer, this should be only possibility is that it should be less and equal to 0. Because 1 by 2 less than 1 by 2, a positive integer cannot be possible. So that's why from this equation, we can derive this is half minus 3 by 4 x3 minus 3 by 4 x4 should be less and equal to 0. So the above equation holds good with the justification that an integer value less than 1 by 2 should be less and equal to 0, because more than 0 it is not possible if you subtract any positive value from half. So the above constraint represents a cut. So this one representing a cut which may provide an integer solution. Now this is for Z row. Come to that your first x2 row. Similarly for x2 row, we can write x2 minus, it was equation was, we can see x2 minus 1 by 4 x3 plus 3 by 4 x4. So minus 1 by 4, always you should make it a plus, the fractional component should be in a with a positive sign. That means you cannot make it a minus 1 by 4 x3, because this is, though it is a less than 1, but it is a fractional value. So you have to make it a minus 1 plus 3 by 4. So you have to always make it a fractional value, a positive one. So that's what we did it. X2 plus minus 1 plus 3 by 4 x3. That means this is equal to minus 1 by 4 x3. And this is a 3 by 4 x4. So this is 0 plus 3 by 4 x4 is equal to 1 plus 1 by 2. Similar way, we have to make all the integer value in the left hand side, and we got this is x2 minus x3 minus 1 is equal to 1 by 2 minus 3 by 4 x3 minus 3 by 4 x4. And accordingly the associate cut is this, that means this should be also less and equal to 0. If this is an integer, this should be an integer, and less than half the integer value is always less and equal to 0. That's why this equation holds. That means half minus 3 by 4 x3 minus 3 by 4 x4 should be less and equal to 0. Now see, in the cutting plane algorithm, the cut having the highest fractional value should be used in first for obtaining the integer solution. In this case, both the cuts having the same fractional value, that means equal to 1 by 2. So here you can see in the x2 row, the cut fractional value is 1 by 2. And if you see the Z row is also the fractional value is 1 by 2. So in the right hand side, the fractional value is all in both the cut, it is 1 by 2. So whichever, if there is a tie, you can arbitrarily choose either one. If it is not equal, then the higher fraction should be considered first to obtain the solution at a faster rate. That means at a faster rate, though you can get, if you choose the second one, that means lowest one, you can get the solution, but the iteration will increase. So we have to choose the, where the fractional value is highest, we should choose the first that cutting plane. So here, since either one, both the constraint, both the cuts having the same fractional value, we have chosen this this cutting plane, that's x2 row, and this is equal to minus 3 by 4 x3 minus 3 by 4 x4 plus s1. This is a, to make it a equality constraint, this s1 is a slack variable, and that is also slack variable should be greater and equal to 0 and integer. So this is what from here we are getting this plane. So we are considering the second constraint, second cut for this, first adding in that your optimal solution. Now see how we can add here. What was the final simplex table we have obtained? It was that except this row s1 and this column s1, it was there the final simplex table. We have added this in the final simplex table. We have added one row with s1 and one column with s1. And this wire, if you compare with the final simplex table, this was 1 0 1 by 2 minus 1 by 2 3, and it was 0 1 minus 1 by 4 3 by 4 is equal to 3 by 2. And for Z row, it was 0 0 3 by 4 7 by 4, and it was 39 by 2. Now if we add that s1 row, that means this constraint, this plane, we have to add it in the final simplex table, because every time if you are adding the constraint, you don't require to solve afresh from the starting point. In the final simplex table, we are adding the cutting plane. And here s1 row, in the s1, this constraint, if you see the coefficient of x1 is 0, coefficient of x2 is 0, and coefficient of x3 is minus 3 by 4, coefficient of x4 is minus 3 by 4, coefficient of s1 is 1, and right hand side value is minus 1 by 2. So here we can see S1 coefficient of x1 is 0, coefficient of x2 is 0, coefficient of x3 is minus 3 by 4, coefficient of x4 is minus 3 by 4, and coefficient of S1 is equal to 1, and right hand side value is minus 1 by 2. Now this is the table, revised simplex table we got with one additional constraint we have added in the final simplex table. Now you have to obtain the solution again, you have to make the iteration. Now you can see in this table, in the right hand side, there is a negative value. That means this is the table is optimal, but infeasible. This is not, because your all the variables are non-negative in nature. And if you are getting any negative value, S1 is equal to minus 1 by 2, this is an infeasible, this will give you an infeasible solution. So we have to apply for this type of problem, we have to apply a dual simplex algorithm. And in the dual simplex algorithm, because in the dual simplex algorithm, we have reached, we generally started from the optimal solution and we have moving towards the feasibility. So that's why this is an optimal but not feasible. So we have to move towards the feasible reason. So in the dual simplex, as I told, first you have to decide the leaving variable, and the leaving variable is the -1, maximum -1. Here it is the S1 row is the leaving variable, is the S1 variable. It will leave the basis, and which one will enter? The ratio. This means ratio is equal to Z row divided by that your pivot row, and only for the negative coefficient. So only these two are negative coefficient, x3 and x4. So we have determined for this x3 and x4. These are the only candidate to enter the basis. So this is equal to 1 and this is equal to 7 by 3. So the minimum one will be the entering variable. So this x3 will enter the basis, that means S, and replace the S1 from the basis. So if we again in the similar process, we have to do that your new pivot row is equal to old pivot row divided by the pivot coefficient, and this is minus 3 by 4. So this is 0, this is 0, this is 1, this is also 1, this is minus 4 by 3, and this is 2 by 3. And all other row is equal to old row minus pivot row into new pivot column, old row minus pivot column coefficient into new pivot row. So in that way, we have transformed, we have converted yes. So we have obtained the revised simplex table. This is S1 is replaced by X3, and we got accordingly using the Gauss-Jordan transformation, we obtained the solution. And this is now X1 is equal to 8 by 3, X2 is equal to 5 by 3, and X3 is equal to 2 by 3, and Z is equal to 19. So we got the integer solution, but still the decision variables X1 and X2 are non-integer in nature. That means yet you have not got that integer solution. Now again, in the above simplex table, we can see the fractional component of all the three rows are 2 by 3. So here if you divide this fractional component, this is 2 plus 2 by 3, this is 1 plus 2 by 3, and this is 2 by 3. All are equal. The fractional components are equal. So either of the row you can use to derive the cutting plane. You can consider once again you have to derive, apply the same method to add new cutting plane in this solution. Now how to derive, from which one you should consider to derive the cutting plane? So since all the row there is the fractional component is equal, that means 2 by 3. So either of the row you can use as a source row to derive the cutting plane. So here we are using the x3 row to derive the cutting plane. So x3 row is what? We can get x3 plus x4 minus 4 by 3 s1 is equal to 2 by 3. So x3 plus x4 minus 4 by 3 s1 is equal to 2 by 3. And what we can write? x3 plus x4 and this minus 4 by 3 is equal to minus 2 plus 2 by 3. As I told that you have to always make the fractional component as a positive one. So this is a minus 2 plus 2 by 3 is equal to minus 4 by 3 into s1 is equal to 2 by 3. So we can get it that in a similar way we have to left hand side should be an integer, all the integer value, that means x3 plus x4 minus 2s1 is equal to 2 by 3 minus 2 by 3 s1. So if this should be an integer value, that means 2 by 3 minus 2 by 3 s1 should be less and equal to 0, because less than this 2 by 3 s1 is a positive value. And if you make a require an integer value less than 2 by 3, it should be less and equal to 0. And that's why 2 by 3 minus 2 by 3 s1 is less and equal to 0. This equation associate cut can be derived. And if you make it a equality constant, adding a one slack variable again s2, so we will get minus 2 by 3 s1 plus s2 should be equal to minus 2 by 3, where s2 is greater and equal to 0, an integer. So again, this cutting plane, this plane you have to add in the last simplex table you have derived. And this was the simplex table you have derived, and only except this s2 row we have added here and s2 column we have added here. So s2 row, the coefficient of x1 is 0, coefficient of x2 is 0, coefficient of x3 is 0, coefficient of x4 is 0, coefficient of s1 is minus 2 by 3. So correspondingly I have put it here, coefficient of s1 is minus 2 by 3 and coefficient of s2 is 1, and right hand side value is minus 2 by 3, and all other values remain same. So here the coefficient of s2 in x1 row is 0. So in all other row, the coefficient of s2 will be equal to 0, because you have not added this slack variable in other constraint. So this will be automatically 0. Now here again we can see this is an optimal, but again infeasible, because the right hand side value of s2 row is minus. So this is an infeasible solution. So again you have to apply the dual simplex algorithm to replace this to obtain the feasible and optimal solution. And you cannot make sure that how many cut you have to require to add to obtain the integer solution. So you have to do the similar type of iteration till you are obtaining all the solutions, all the values x1, x2, x3 are in integer solution. So here we are again applying the dual simplex algorithm. So first we have to identify the leaving variable. So only this, it is one value, one right hand side is a negative one. So this one s2 is the only option. So this will be replaced. This s2 will replace from the basis. Which variable will replace? Only one negative coefficient in the pivot row. So this is minus 2 by 3. So this is S1, corresponding to the S1 is only one negative coefficient in the S2 row, pivot row. So this S1 will replace the S2 from the basis. So this one will be the entering variable and S2 will be the leaving variable. And again the similar transformation we have to do. New pivot row is a old pivot row divided by the pivot coefficient, and this is 0, 0, 0. This is 1, this is minus 3 by 2, and this is 1. And all other row is equal to old row minus pivot column coefficient into new pivot row. So if we derive this table, we can get after that. And you can find here all are non-negative in the nature, right hand side are non-negative in nature. So that means this is a feasible solution, as well as here no negative value in the Z row, we got it. That means this is also an optimal solution. So here this is an integer feasible optimal solution we have obtained here, and value is x1 is equal to 2, x2 is equal to 2, x3 is equal to 2, s1 is equal to 1, and z is equal to 18. So the optimal integer solution is, because our decision variables are only x1 and x2, so z is equal to 4x1 plus 5x2 is equal to 18. Now if you recall, the branch and bound algorithm, we got the same solution as an optimal integer solution, and that was x1 is equal to 2 and x2 is equal to 2, and z was 18 was the optimal integer solution using the branch and bound algorithm we have obtained. So the same solution we got it from the Gomori's cut method or cutting plane method. So this is the algorithm we got it. Now, if we represent this problem just graphically, just to explain that, because if you there is a more than two variable, you cannot represent graphically. But since it is a two variable problem, I just to make it a better explanation of this problem, you can just see this graph. This was an x1 um, axis. This is an x2 axis. So this is the constraint one. This was 3x1 plus 2x2 less than equal to 12. So it is intersecting that x2 at 6, intersecting x1 at 4. And this is the constraint 2 intersecting, this is x1 plus 2x2 is less than equal to 6. So intersecting x1 at 6 and x2 at 3. Now the solution, we got this was the intersection, this was 3 and 3.3 by 2 was the optimal solution if we are not considering an integer solution. So that was, we got it, we have already explained that. Now how the cutting plane is derived. Now if you see, if you recall just here that how the constraint we have added. So from that your x2 row, we got it, we have taken this is half minus 3 by 4 x3 minus 3 by 4 x4 is less than equal to 0. What this is indicating, because this is x3 and x4 also the slack variable introduced in the original integer linear programming problem. So if x3 and x4, if you go to that your initial equations, just I am again showing you. Yes, this is 3x1 plus 2x2 less than equal to 12. That means this was 3x1 plus x2 plus x3 is equal to 12 to make it equality constraint. So this x3 is the slack variable in constraint 1, x4 was the slack variable in constraint 2. So what is the value of x3? x3 is equal to 12 minus 3x1 minus 2x2, and x4 is equal to 6 minus x1 minus 2x2. So if we have to represent this cutting plane in terms of x1 and x2, we can get what happened. So here you can see this half of minus 3 by 4 x3 minus 3 by 4 x4 relation equal to 0, and x3 we have derived from that first constraint equation that was 12 minus 3x1 minus 2x2, and x4 is equal to 6 minus x1 minus 2x2 relation equal to 0. So this is, if you simplify this equation, you will get x1 plus x2 relation equal to 13 by 3. Now, if you draw this constraint line, this cutting plane, that means we have added in that simplex algorithm this equation directly. Now, if you derive in terms of x1 and x2, the cutting plane is x1 plus x2 relation equal to 13 by 3. And if you draw here in this, so this is x1 plus x2, this blue color line, this cut one, this is x1 plus x2 relation equal to 13.3. That means x1, it will intersect 4.33, and here it is also 4.33. So it will, now here if you see the intersection point, it will intersect the constraint 1 line at this point 8 by 3 and 5 by 3, and here this is constraint 2, it will intersect at 8 by 3 and 1. That means cut 1 will not provide you the integer solution, and that's why a second cut we have introduced, and that was 2 by 3 minus 2 by 3 s1 is less than equal to 0. And from here we can derive this is s1 is greater than equal to 1. And if we put this s1 value from that your original constraint equation, we will get this is minus 2 by 3 plus x3 plus x4, 3 by 4 greater than equal to 0, 1. And again, if we put x3 plus x4 value, we can get this equation. And if we simplify, we can get the equations in terms of x1 and x2. It is x1 plus x2 less than equal to 4. And this is the second card representing by that your blue color line. Again, it will intersect a second of constraint 1 at this is 40, and then constraint this constraint 2 at 2 2, and here we are obtaining the optimal solution. That means x1 is equal to 2 and x2 is equal to 2. That means how the cuts we can derive in terms of x1 and x2, but instead of every time you don't require to derive in terms of x1 and x2, because if the problem move on in every iteration, we are directly deriving, generating the cutting plane from the last simplex table, and it is difficult to every time calculate. And even if you are not able to present in the graphical method if there is a more than, if there are more than 2 variables. So here, just to represent that how the cutting planes are introduced, this can be derived from the revised simplex table. Every time you have to introduce one cut to narrow down the search and finding an optimal solution. And that is what we, using that Gomori's cut method, we can obtain. Using this simplex method, we can get that your integer solution of the problem. So this is what that your Gomori's cut method for solving the integer programming problem. And we have explained the your branch and bound algorithm, and this is one cutting plane method. I think 2 algorithm is enough for understanding what is the difference of this integer programming from the simple linear programming. Here the differences is that if you are restricting the variables into integer values only, then your problem is called that your integer programming problem, because this is also linear in nature. And if you are not restricting your variables to integer, then it is a linear programming problem. And here we have discussed the category types of problem. One is that your binary conditions, how that, or normal pure integer programming problem. So here, this is all the variables we have considered that as a integer variable. That means this is a pure integer programming problem. We have not discussed if we have to deal with, sometimes you have to face that only some of the variables. Suppose if you are restricting only x1 is an integer and x2 is not an integer, there is no bound for x2. It can be fractional, it can be integer. So in that case also you have to deal separately in a different way, that how to solve an mixed integer programming problems. So if time permits, I will discuss with some example with for mixed integer programming problem also. So we have discussed the pure integer, we have discussed the binary integer programming algorithm using that branch and bound algorithm using the cutting plane methods. Now, if you have any questions, you can ask to me.